Hello and welcome to Weapons of Math Instruction. This is the second in my series of videos on uncommon integration techniques. And in this installment, I'll be talking about how to use Euler's identity as a technique of integration. In the first segment, I'll state Euler's identity and give a quick rundown of how it can be derived using the methods of Calculus 2, namely power series. So Euler's identity is e to the ix equals cosine x plus I sine of x, where I is the square root of -1, aka the imaginary unit. And this identity is remarkable in that it relates the exponential function in base e to the cosine and sine functions. And it's noteworthy that this relation wouldn't be possible without going beyond the real numbers and into the complex domain. We can derive Euler's identity by considering the Maclaurin series of each of these functions. Here's the Maclaurin series for the sine function. Notice that all the powers of x in this series are odd. This makes sense because sine is an odd function of x. Here's the Maclaurin series for the even function cosine x, and not surprisingly, all the powers of x in this series are even. And here's the Maclaurin series for the function e to the x, which is neither even nor odd. And so, unsurprisingly, this series contains even and odd powers of x. So what we're going to do next is plug in ix in for x into this series for e to the x, and give it a shake and see what falls out. And so here I've done the substitution. You can see that I've replaced each x with an ix. So let's keep turning the crank. Here in the second degree term, we're squaring an I. So recall that I is the square root of -1. So when you square I, you get -1. And that -1 is right here. When you cube I, you get -I. That -I is right there. When you raise I to the fourth power, you just get 1. And so ix to the fourth over 4 factorial is just x to the fourth over 4 factorial. And after the fourth power of I, the powers of I just cycle through the same values. I, -1, -I, and 1. So notice, all the terms of even degree are real. And all of the terms of odd degree are imaginary. So what we're going to do is separate the real and imaginary parts in the series and see what we get. So I grouped all the real terms in the first set of parentheses. And for the imaginary terms, I pulled out the common factor of I and put all the terms of odd degree in the second set of parentheses. And these two groups should look familiar. In the first set of parentheses, I have the Maclaurin series for the cosine function. And in the second set of parentheses, I have the Maclaurin series for the sine function. And so that completes the derivation. E to the ix equals cosine x plus I sine x. And just as an interesting little aside, let's plug in x equals pi into Euler's identity. So e to the I pi equals cosine pi plus I sine pi. Now the cosine of pi is -1 and the sine of pi is 0. So I've gone ahead and evaluated those. And so e to the I pi equals -1. Now if I add 1 to both sides, I get a neat little identity. E to the I pi plus 1 equals 0. And this identity is remarkable because it relates 5 important numbers. The additive identity 0, the multiplicative identity 1, 2 of the most important irrational numbers, e and pi, and the imaginary unit I, all in one equation. If you've been following me for long enough, you know how important I consider e and pi to be, because I put out a total of 17 videos in celebration of Pi Day and E Day grouped into 3 playlists. If you're interested in learning more about these famous numbers, dig into my video library and go through those playlists. Now, if you're a calculus instructor, you've undoubtedly already seen the derivation presented in the first segment. And if you're a student who's taken Calculus 2, you might have seen your instructor present that derivation. What I want to show you in the rest of this video is how Euler's identity can be used as a technique of integration. We'll start by considering these two integrals, the integral of e to the x sine x dx and the integral of e to the x cosine x dx. These integrals are standard examples in Calculus 2 as they require not one but 2 integrations by parts. They're also interesting because they require one to algebraically solve for the value of the integral after integrating by parts twice. There are also a lot of work when done that way. We're going to use Euler's identity to cut through these 2 integrals like a hot knife through butter. So here I've repeated the 2 integrals for reference. And in light of what I covered in the first segment, it shouldn't come as a surprise that we're going to use Euler's identity. After all, Euler's identity relates the exponential function in base e to the cosine and sine functions, and that's just what we have in these integrands. So to proceed, we'll consider the integral of e to the ix e to the x dx. And this integral is going to be a lot easier than the 2 integrals in the line above because we can take advantage of the rules of exponents. And here I've done just that. I've combined the two exponentials in the integrand to get e to the 1 plus I times x. And this function is easy to integrate. We get 1 over 1 plus I e to the 1 plus I times x plus c. And we can clean this up a bit. So I'm going to rationalize the denominator of this fraction by multiplying the top and the bottom by the complex conjugate of the denominator. And here I've separated the exponentials into a complex factor and a purely real factor. Now in this step, I've explicitly used Euler's identity by replacing e to the ix with cosine x plus I sine x here and here. And in this step, I've FOILed out the product of 1 minus I and cos x plus I sine x to get all of this, these four terms right here. Now let's collect the real and imaginary parts together. So on the left side, I've split this one integral up into two integrals. The first integral is purely real, and the second integral is purely imaginary. And here, I've done what I just said I was going to do. I've collected the real parts right here, and the imaginary parts right here. Now I'm running out of room, so I will carry this last line here up to the top of the next slide, like this. Okay, here we go. So this is a complex function of x, and this is a complex function of x, and they're equal to each other. And two complex functions of x are equal to each other if and only if their real parts and their imaginary parts are equal. So we're going to equate the real and imaginary parts individually. So when I equate the real parts, I get the integral of cos x e to the x dx equals 1/2 cos x plus sine x all times e to the x plus c. And if I equate the imaginary parts, I get integral sine x e to the x dx equals 1/2 sine x minus cos x all times e to the x plus c. And that's it. We're done. We calculated the two integrals that we set out to calculate. So, by using Euler's identity to evaluate the integral of e to the ix e to the x dx, instead of using integrations by parts to evaluate these two integrals individually, we got two integrals for the price of one and with a lot less work. So I hope this adequately illustrates the power of using Euler's identity in situations like this. In the last segment, I used Euler's identity to evaluate two integrals that every Calculus 2 student sees. In the next segment, I'll use Euler's identity to evaluate two integrals that most likely no Calculus 2 student has seen. The integral of the cosine of the ln of x dx and the integral of the sine of the ln of x dx. Now you might be thinking, whoa Nelly, Euler's identity doesn't mention natural logs. True, but it does mention the exponential function in base e, and the natural log is its inverse function. We will exploit that relationship. So here I've repeated the two integrals for reference. And we're going to consider the integral of x to the I dx. So this is easy to integrate. We just use the power rule. So integral of x to the I dx is 1 over I plus 1, x to the I plus 1 plus c. And believe it or not, at this point, the integration is done. We just need to clean this up. So in the next step, I'm going to rationalize the denominator of this fraction by multiplying the top and the bottom by the complex conjugate of the denominator. And here I've separated x to the I plus 1 into this factor x as purely real, and this factor x to the I that is complex. And after cleaning up that fraction, I get 1 minus I over 2 times x to the I plus c. Now, for positive values of x equals e to the natural log of x. And this is of course due to the fact that e to the x and the natural log of x are inverses of each other. Now I'm going to pull a rabbit out of my hat. I'm exponentiating both sides of this equation to the power of I to get x to the I equals e to the I ln of x. Enter Euler, stage right. We can use Euler's identity with the natural log of x in the place of x to get this right here. So x to the I equals the cosine of the ln of x plus I times the sine of the ln of x. And the real and imaginary parts of this guy are nothing more than the integrands of the two integrals at the top of the slide. And we've already integrated x to the I. So here, I've rewritten the integral of x to the I dx by substituting this expression in for x to the I here and here. All that remains is to split this thing up into real and imaginary parts and equate the parts. Now, I know that this is a lot to look at, so I'm going to tidy this up a little bit. I've collected the x over 2 right here, and here I've written the two binomials, 1 minus I and cos ln x plus I sine ln x. And in the next step, we're going to FOIL this out. So when I do that, I get these 4 terms in brackets right here. Now I'm running out of room, so let's go to the top of the next slide. So this is just the last line from the previous slide. I just recopied it. So in this step, on the left side, I have split this one integral up into 2 integrals. The first integral is purely real, second integral is purely imaginary. On the right side, I've collected the real parts here and the imaginary parts over here. And I just bet you know what I'm going to do next. Yep, you're right. Let's finish this. When I equate the real parts of this thing, I get integral cosine of ln of x dx equals x over 2 cosine of ln x plus sine ln of x plus c. And when I equate the imaginary parts, I get integral of sine of ln of x dx equals x over 2 sine of ln x minus cosine of ln x plus c. And that's it. We got them both. Once again, we got 2 for the price of 1. Thanks for tuning in to Weapons of Math Instruction. I'll talk to you again in a couple of days about another integration technique that you don't find in calculus books. Bye-bye. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.